So let's start with the topic, which is mechanism first. So what is a mechanism? If you see any moving parts, or rather assembly of moving parts moving together, they form a mechanism. Now if you see on your screen on the left, this is a screw jack. Where you can see the screw jack, if you open the trunk of your car, you will observe that a tool is present that is used to lift your car when your tire punctures. So this is a mechanism that is used to raise your car. If I play the animation here, you see there is a screw that is being rotated. Here there is something fixed, and you see this link. This is rising so that it can raise the load. In this case, it would be your car. So this is a screw jack. We can animate this in NX, and some other animation can also be done. So this is one example, and coming to the next example that we have is this. This is a saw. This is used in cutting. So if you see the animation here, there is some mechanism here which is rotating, and the final result that I'm getting is this translational cutting in this direction, which we can achieve in this NX simulation software, right? So these were the two examples of simple mechanisms. Let's move forward. Now, when you start with the simulation, you will be presented with a prompt where you will select the type of analysis that you are going to use. So there are two types. The first one would be kinematics and the other one would be dynamics. I'll tell you the difference in short. When you are dealing with the kinematics, means you are only concerned with the motion of the body, right? I'll try to write here with my mouse. Excuse me for my bad handwriting. So this would be based on motion only. That means there is no point of gravity acting in this mechanism. I am making G as gravity. So this means that we are only interested in the simulation of a mechanism. We are not dealing with the mass of the body. That is only movement we are considering. And if you see this other type of analysis, this is dynamic analysis. We'll take this when we want to consider the mass present in that mechanism. So when a mass is present, that analysis would be dynamic. So when the mass is present, that means we can also interact with the forces, or we can calculate the forces or torque or reaction forces and all. So this would also be used in our simulation when we move forward, and I'll cover kinematic simulation also, right? Next we have some nomenclature which will be used again and again, so it would be better and important if we discuss this in the introduction of this course. So the first one is link. Link is a nomenclature used in NX version that is before 12 or 12, beyond 12 or after NX 12. This term has been replaced by this term. Everything else is completely same. So what is link or motion? It is an object that require motion. So if you see on my screen here, this is an object, this will require some motion. This is also an object, this will also require some motion, and this is also an object which will require some motion. I'm not talking about the direction of this motion now, just believe that when the mechanism plays, these link would be in motion. It could be translatory or it could be rotational. And we see here, this is also a link, but it's a fixed link. So this definition is not complete. So what link is, that can move or that can remain fixed. Okay, so this is a link, this is fixed here, and these links can be moved, right? We'll perform the practicals when we move forward. You just have to remember these certain nomenclature so that our journey becomes easier. Coming back, we have this joint here. What's a joint? Joint is actually this. If you see the connection between the two links, this is a joint. If you see here, these two links, motion link and fixed link, are connected by this joint, and if you come here, this is the joint. So what joint does is that it provides a relative motion between two links, right? Now the next term is constraint. Constraint means we are restricting the motion using the joints. So when I applied a joint here, it has restricted the motion of these two links. How? This link could go here also, it could rotate like this, and so on. So what I've done here is I have proposed a special joint here which you don't know about, that we'll discuss in the slide afterwards. When you provide a joint at a location, you are constraining the motion, that is, you are stopping it to rotate or translate in another axis. Okay, so this is constraint. Next is a very important term, that is degree of freedom. It simply means number of linear or rotational movements that a body can make. So if you see on your screen, this is a body that is present in 3D space. I'll also draw a coordinate system here quickly. This would be my Z, this is X, and this would be Y. Now if you see this body is allowed to translate here and here in X direction, this is X. If you also see, this body can also translate in Y direction, which is this one. It can also translate in Z direction. So three translation can take place, which I'm defining as 3T. Plus, if you see this body, this can also rotate around this axis, which is Z. The same case is with the X and Y axis. So three translation and three rotation. That means for a body in space, we have around, not around, exactly, total 6 degree of freedom. That means this body can either translate or rotate in any of the direction based on the joint that we are going to use in the future. So the body will have 6 degree of freedom in total, and we are going to restrict that to achieve our desired motion, right? Next is Grubler count. So in NX we cannot directly show the degree of freedom of a mechanism. Instead we use Grubler count. Grubler count has an equation here which involves links, degree of freedom removed by joints, and this motion driver input that we'll see in the future. Actually, you don't need to remember this equation. You just need to remember that when we are talking about Grubler count, there are three cases: 1, 2, and 3. Now, if you see here, this is case number 1. When the Grubler count is less than 0, it is going to be a case of redundant constraint. What redundant constraint means is, if you see this figure here, this part is fixed using this one joint, right? So it has made some constraint. The same constraint has been applied using these two joints also, which was not necessary. That means I'm using these two joints here to restrict the same motion that this first joint was restricting. That means these two constraints are redundant. So in that case, our Grubler count could be less than 0. Okay. I'll come to this when we talk about this in the practical. You just have to listen to this so that you get an idea what Grubler count is. Otherwise, when we move forward, we are going to make the practical out of this. Second case is when the Grubler count is greater than 0. In that case, it means your body is not restricted and it can move in various directions, right? And the third case is when Grubler count is equal to 0. That means your body is fully constrained. Now this is the actual case. Actually, this is the ideal case. We will try to achieve this, but the main important thing is you will mostly have this type of case when your Gruber count is less than 0. That means it can be negative. So the good thing about NX is even if your Gruber count is less than 0 or it's a case of redundant constraint, it will automatically remove the effect of these two redundant constraints in this case, and it will give you the output accordingly. So you don't need to worry about removing the extra constraint. You can depend on NX because it can remove the redundant constraints automatically. So we'll try to achieve this Gruber count 0, but if you are not able to, then you don't have to worry. NX will automatically ignore this, right? Let's move forward. Now we'll talk about some joints. So the first type of joint that you are seeing here is a revolute joint. Revolute joint has only 1 degree of freedom. It can only rotate in axis. It could be any axis, right? So it has 1 degree of freedom, and that is rotational. Now if you come to the second joint, that is slider joint, or it is also known as translational or prismatic joint. It also has 1 degree of freedom, and it can only translate in one direction. It could be any direction, but it should be translational only. So I'm naming this as 1T. The other one is cylindrical joint. It has 2 degree of freedom, one translation and one rotation, and that is also based on the same axis. So suppose Z is my translation axis, so it is allowed to rotate in the about the Z axis only. So 2 degree of freedom, one translational and one rotational. Screw joint, this is a special joint. So in this joint we have 1 degree of freedom. Actually you don't have to confuse this with the cylindrical joint. It has one rotation and one translation, but this is a combined motion. So this is 1 degree of freedom, not 2, right? Next we have universal joint. If you see this body here, this is the action link, and body number 2 is the base link with which one is connected. So if I talk about this one body, it has a universal joint here. That means it has 2 degree of freedom, and in this case or any case of universal joint, in the mutually perpendicular axis it can rotate about those. So 2 degree of freedom, both are rotational. So I'm writing here 2R. Now we have a spherical joint. Spherical joint has 3 degree of freedom, and all three are rotational in their or about their axis. So three rotations, all are rotational, right? Now we come to this planar joint. So planar joint has 3 degree of freedom. If you see this body here, and it is resting on this body actually. So if you see, this body can translate in this direction, as well as rotate about its own axis. So it has 3 degree of freedom, 2 translational plus 1 rotational, right? Now the last joint, which is fixed joint, this is actually not a right prediction or representation of the fixed joint. This is actually a slider joint that you are seeing here. I did this by mistake. This has to be a fixed joint. That means it cannot move in any of the direction. This means it has 0 degree of freedom. I'm writing this as DWF, DOF. Forgive my writing, I'm using my mouse here. So it cannot move in any of the direction, whether it is translational or rotational. So this has 0 degree of freedom, right? Moving forward, we have some specialized types of joints, and we are going to actually define or make these joints in the practicals when we move forward. So the first type of joint or a coupler is point on curve. If you see this diagram here, I'm making this curve and I'm making this diagram, which is also a link, and there is a point connection here. So if you see here, this is point on curve constraint. This curve and point are constrained. So this will remove 2 degree of freedom. It won't allow 2 degree of freedom. It will actually remove 2 degree of freedom, right? There's a difference. Next is curve on curve. From the name itself, you can figure it out. When the curve is resting on the other curve, this will be our curve on curve constraint. The next one is point on surface. So suppose this is my surface and this is a point. The constraint between them would be given using this point on surface, right? Next is our gear coupler. By the way, you can see the degree of freedom removed in this column, right? So now coming back to gear coupler, suppose we have these two gears meshing with each other. We can apply a constraint known as gear coupler. We can constrain these so they can only rotate and there's a point of contact between them. The next one is rack and pinion. Suppose this is a pinion gear and this is one gear which is infinitely long, or it could be of any length. So the connection between them would be constrained using rack and pinion coupler, right? So this also remove 1 degree of freedom, right? We'll move forward. Now, when you perform the simulation, you don't actually have to solve anything. Everything is done behind the screen using the solvers. What solver does is, solver solves some equation of motions and that contains force, torque, acceleration, displacement, etc. So there are four types of solver that you can see in NX simulation: SimCenter, NX Motion, Recordine, and MSC Adams. I won't take much of your time here because we are going to simply use it by just selecting this, but still I'll give you some introduction. SimCenter has some limitation that it doesn't support 2D contact and joint friction is also not available. And if you see the file extension of this, this would be .mres or .minf, right? And what PMDC motor here means, I think it stands for permanent magnet direct current motor, which is also used in simulation, although we are not going to use it. So this solver doesn't support these things. Coming to NX motion solver, the file extension that it uses is .sim. We are going to deal with this, but it also has a drawback that some certain industries that use tires and rods, that we won't be able to use, and some flexible links also we cannot use when you are using this type of solver. And co-simulation, that means when you are importing control system for some from some other softwares like MATLAB, you cannot do that. Next, coming back to the other solver, which is Recordine. Recordine is will be used for the dynamic simulation. We are also going to use this in our tutorial series, and this contains these many file types. So these file types, or one of them or more than one of them, would contain the equation of motion and their result here, if you see by the definition it goes. And last we have the MSC Adams, which has the file extension as .res. This was acquired by Siemens, so we can use this solver also, right? Next, there is a term called driver. That means the motion that we are going to give to a mechanism is defined by a driver. So we have four drivers here, although we have more than these four drivers when you open your NX screen and go into the driver tab. So the first one is polynomial. Polynomial is actually a curve which is based upon some quantities, that is displacement, acceleration, jerk, etc. So the motion would be based on this curve defined by these parameters. We can also define these parameters. This will mainly be used when you are going to provide motion to a cam profile or robotic arm, right? Coming to harmonic motion or harmonic driver. If you remember your school days or high school days, you must have seen this diagram. This is a sinusoidal curve and this is some amplitude. This is complete one cycle, if you remember. So the motion provided by this driver would be oscillating motion like that of what you see in a pendulum. So the motion would be harmonic or rather oscillatory. You can observe that when we perform this simulation. Coming to articulation, you can just provide the driver or motion, whether it could be translatory or rotationary, to a joint here. The most common example here would be applying this driver to a 4 bar linkage, which we are going to do in this series. So you can apply the motion here or anywhere else on this joint, and this becomes a driver. Last we have function. So the driver here defined is based on a mathematical function. It could be sine, log, tan, etc. You can define your driver using these mathematical functions. So we have many options to define the driver, and we are going to see each one of them when we are going to perform the simulation. Next. So these are the steps that we are going to use when we are actually going to perform some simulations. Some are optional and some are mandatory. We'll see how it goes. So the first thing would be obviously to import or open the simulation file if you already have the simulation file. The next thing would be to add the links which I had showed you earlier in the page. When the links are applied, when we are going to place some joints, I told you about the types of joints that are available. Based on your simulation, you are going to provide the joints, and then we are going to provide a driver. We saw the list of drivers that are available. You can use any one of them based on your simulation. And then we are going to use a connector like gear coupler, etc., or rack and pinion. Next, we can add markers and sensor. This is an optional step. So for marker, if I tell you, you can place a coordinate system on your sample and see the reference. And for the sensor, if I tell you, you can place a sensor for linear or angular displacement, and when the motion is taking place, the value of these or those will also change. So we can provide a sensor here on your mechanism. Then we can also apply a load in the form of weight or force, and then we'll perform the analysis. Next step would be to create a solution where you will define the number of steps or the time in your kinematic simulation or dynamic simulation. At last, we'll solve the solution using the solver that I had discussed earlier. And at the last, we can plot the result using a graph. This graph could be anything, whether it is force, torque, displacement, acceleration, etc. So these are the steps that we are going to perform in our simulation, and this would be the order of the steps. We can omit some of the steps that we do not need in our simulation, but this is the workflow. Now if you want to explore other courses, I have this link here. If you see to my left, you can scan this QR image and you can directly go to that website. And if you scan the right side of my screen, you will see there is a QR to log on to my YouTube channel. That also you can do, and here are the courses that I teach. So yes, we are ready to simulate some results. See you in the simulation, and let's dive into the practicals.